Today, we're going to talk about a really revolutionary kind of steel. One that was specifically designed to solve a paradox that's been bugging engineers for like over 100 years. It's a fantastic story about a spectacular failure that led to this massive scientific breakthrough, and in the end, an impossible material that was made real. Steel has always had this dangerous weakness hiding inside it. And that quote from Dr. Zhivago, that's not just some fancy literary flair. No, it points to a very real, very high-stakes problem. Because when the temperature plummets, the very stuff that holds our world together can literally become as fragile as glass. And that, of course, can lead to catastrophic failure.
And that brings us right to the heart of the problem, what I like to call the perfect steel paradox. See, it's this constant struggle to balance two absolutely essential properties that, well, they just naturally want to work against each other.
Okay, so here's the fundamental trade-off. You can make steel incredibly strong, right? But that almost always comes at a cost. And that cost is toughness, its ability to actually resist breaking. Think about it. A super strong but brittle rail, it's like a glass hammer. It just shatters on impact, especially when it gets cold. And this is the exact problem engineers have been wrestling with for more than 100 years.
So why is the conventional steel that you use for rails, it's called perlite, why is it so vulnerable? Well, to really get what's going on at the microscopic level, we need a simple analogy. It's a bit strange, but stick with me. Picture a cabbage floating in a bucket of water. Okay, so in this analogy, those cabbage leaves, they're like one big interconnected crystal of this really hard, brittle stuff called cementite. And the water all around it, that's a much softer crystal called ferrite. Now here's the problem. Because the whole thing is linked together, if a tiny crack starts on one end, there's nothing to stop it. It can just travel straight through the whole colony. And that's what makes this structure so incredibly weak when it comes to fractures.
So, to solve this problem, scientists came up with a pretty radical idea. They imagined a brand new kind of steel, one that just completely got rid of those brittle parts altogether. They dreamed of a material that was totally carbide-free.
On paper, this new bainitic steel looked like a miracle. Its structure was ultrafine, which should give it both strength and toughness. It had these special films of another phase called austenite that were supposed to act like fire brakes, to stop cracks dead in their tracks. And with no brittle cementite to start the trouble, it should have been incredibly damage-resistant. It was, in theory, the perfect cure-all for steel's biggest headaches.
But when this dream material was finally made in the lab for the first time, theory collided head-on with reality. And let me tell you, that dream, it turned into a nightmare fast.
So after all that incredible theory, all that promise, was this the steel that was finally going to solve the paradox? Nope. It was a complete and utter failure. The toughness was, and I'm quoting its own creator here, terrible. And it wasn't just bad, it was totally unusable. See, its impact transition temperature, that's basically the point where it goes from tough to brittle, was over 100 degrees Celsius. This stuff was fragile even on a hot summer day. It was completely, utterly useless for any real-world application. So what went wrong? Well, the investigation found these big, unstable blocks of that good austenite were actually transforming under stress. They were turning into a totally different thing, this untempered, super brittle martensite. And these things acted like tiny little bricks scattered throughout the steel, starting cracks all over the place. Isn't that ironic? The very thing that was supposed to help was actually causing the whole thing to fail. Okay, so to figure out why this was happening, the scientists had to go all the way back to the drawing board, back to the fundamental thermodynamics of steel. And the answer, as they discovered, was hiding in something called the T0 curve.
The easiest way to think of the T0 curve is like a thermodynamic point of no return. It's a hard limit. For the steel to form the way it's supposed to, the carbon concentration in the austenite has to stay below this line. The second it tries to cross that line, bam! The whole process just slams to a halt.
And that's exactly what was happening here. The chemical reaction was hitting that T0 curve and just stopping dead in its tracks. And that left behind those big, unconverted blocks of austenite, which, as we now know, were the real root cause of the steel's awful brittleness. But here's the beautiful part. Once they understood the problem, they knew the solution. They figured out a simple three-step recipe to basically trick the T0 curve. They realized if they reduced the carbon, or lowered the temperature where the transformation happens, or even swapped out some alloying elements, like manganese for nickel, they could push that point of no return further away, and that would give the reaction enough time to finish properly.
So armed with this brand new understanding, they went from a completely failed theory to a material that was ready for some of the most demanding environments on planet Earth.
And the fix itself was surprisingly simple. Guided by their new T0 curve theory, all they had to do was make these small but really powerful tweaks to the alloy's chemistry. Things like just reducing the carbon a bit or swapping out a single element.
And the result, it was absolutely extraordinary. They managed to shift the steel's brittle point from a blistering hot plus 100 Celsius all the way down to a frigid minus 100 Celsius. I mean, that's a staggering 200-degree improvement. And they did it just by understanding the fundamental science. Okay, but what about the real world, right? Well, they put it on a test track in the US. After 90 million tons of heavy traffic rolled over it, the standard old-school rail was severely damaged. And the new Bainite rail, it showed no damage at all.
This success was so profound, so undeniable, that the rail was installed in one of the most critical pieces of infrastructure on the entire planet, the Channel Tunnel, the one connecting the UK and France.
And listen to this, as of 2019, that same rail had successfully carried 1 billion gross tons of traffic, all without any significant issues. I mean, what an incredible testament to a material that started out as a complete and total failure.
When you really think about it, this isn't just a story about steel. It's about a fundamental shift in how we think about materials. It's a shift from just discovering them to actually designing them. By truly understanding the science, right down to the atomic level, we can start to engineer materials with properties we once thought were literally impossible.
Which, of course, leaves us with a really fascinating question for the future. Now that we have the tools to design materials from the atom up, what other impossible paradoxes are out there for us to solve? What other incredible materials are just waiting to be designed, not just discovered?